Welcome to Generative AI Futures.
Today, we are really attempting something I think pretty ambitious.
Yeah, we're diving deep into the actual architectural blueprints for what you might call true autonomous machine intelligence.
Right. This is not about, a small update to an LLM. Our whole mission today is to compare the two dominant and really competing paradigms for building world models.
And world models, just to be clear, are these internal neural networks that an AI uses to learn the basic physics and causality of reality itself. It's how they learn to predict the future.
Exactly. And the two contenders have completely different philosophies.
On one side, you've got the generative approach. This is NVIDIA's huge platform, Cosmos. I mean, it is an engineering-driven beast.
And its goal is a high-fidelity digital twin, a perfect simulation of the physical world.
And on the other side,
You have the predictive approach. This is embodied by JEPA, the Joint Embedding Predictive Architecture, and we'll be looking at its vision language version, VL-JEPA.
and their argument is that photorealism is just a total waste of compute. They want abstract reasoning, not perfect pixels.
So that's the core question for you listening. When you're building an AI that truly understands our world, what's the better blueprint? Is it maximum fidelity or is it maximum efficiency?
Let's get into it. And I think we should start with the challenger, VL-JEPA,
Okay.
because it really launches a pretty aggressive critique of the whole generative idea.
It does. The whole GPA philosophy really starts with what they call the generative trap.
The generative trap.
Yeah, if you look at a standard generative model, its whole job is to predict or reconstruct every single bit of data, every pixel, every shimmer of light. The JPay team basically says this is computationally insane, and frankly, it's just the wrong goal.
It's that classic overhead problem, right? Like if a model is watching a video of someone drinking coffee, does it really need to predict the exact shimmering pattern on the surface to understand that, they're drinking coffee?
Precisely. That is the perfect example. They have a great analogy for this. They say scaling a generator model is like building a taller ladder to get to the moon.
It's just an architectural dead end.
It's a dead end. They argue that intelligence, both human and artificial, is fundamentally about lossy compression. Our brains are constantly throwing away irrelevant details.
Like the exact configuration of leaves on a tree or, the glint of sunlight off a window. We just keep the important, the predictable, the causal information.
All right, so this requires a pretty radical shift in the underlying mathematics.
Okay, so how do they actually do that? How do they formalize this idea of just ignoring the useless data?
Well, they move away from traditional probabilistic models, which really struggle with high-dimensional data, like video.
Because they have to calculate the probability of every single possible pixel configuration,
Yeah.
which is just, it's combinatorially explosive.
It's impossible. So instead, JEPA is built on something called energy-based models, or EBMs.
EBMs. Okay, break that down for us. Give us the non-academic version of that.
Okay, think of it this way. A traditional generative model is like a master art forger trying to replicate a masterpiece down to the last brushstroke. An energy-based model is more like a quality control expert. It doesn't try to draw the picture itself. It just learns an energy function that tells it what doesn't belong. It minimizes prediction error in a very abstract conceptual space.
Not in pixel space.
Not in pixel space. It's just measuring the incompatibility between an input and a potential future.
Ah, so it's a negative approach. It's not about maximizing visual similarity. It's about minimizing conceptual error.
Exactly. The model is forced to predict the abstract latent representation. It learns concept dynamics, not pixel dynamics.
So it has to learn about momentum and trajectory, not just what color the ball will be in the next frame.
Precisely. And if we look at the actual architecture, VL-JEPA, this vision language model, it's built to connect these visual concepts with language understanding.
Okay, so what are the components?
You've got a vision processor that's an encoder that turns the raw video into these efficient embeddings. And then you have a semantic generator, which turns the target text description into a similar kind of embedding.
And in the middle is the predictor, the reasoning engine.
Right, and it's built from transformer layers, like Llama, but its job is unique. It takes the visual input and it predicts the future semantic embedding. It's predicting a language-level concept based on what it sees.
And this design has a huge payoff in efficiency, right? Through something they call selective decoding.
Yes, this is key, because VLJB is always just outputting this continuous stream of semantic embeddings, these pure concepts. It fundamentally decouples the act of thinking from the act of speaking.
I see. So the model can be thinking, predicting, reasoning incredibly fast in the background, but it only pays the computational price of actually articulating its thoughts when it really needs to.
That's it. You only call on the heavy, slow text decoder, the part that turns those abstract ideas into words, when a big semantic shift happens.
And this isn't just theory.
No, not at all. On the EGO-X4D dataset, this selective decoding delivered get this, a 2.85 times reduction in decoding operations and computational costs.
With no loss in output
With
quality.
no loss. That is a massive efficiency win for anything that needs to happen in real time. Robotics, AVs, you name it.
Okay, that is a very powerful case for abstraction, for efficiency. VL-JEPA is like the researcher's model, optimizing for pure speed of thought. So now let's pivot. Let's look at the complete opposite, the generative paradigm in NVIDIA's Cosmos.
Yeah, if efficiency is VL-JEPA's religion, then Cosmos is operating under a completely different mandate. It's about maximum fidelity and really industrial scale.
It's not a research project, it's an engineering platform.
Absolutely. It's built to solve a very specific industrial problem. The massive cost and danger of collecting real-world training data for things like autonomous vehicles or complex robots. You just can't do that cheaply or safely in the real world.
So Cosmos is designed to be a factory, a scalable, safe digital twin of the world where these AIs can train and fail and learn before they ever touch physical reality.
Exactly. And the scale is just immense. It starts with the data. They begin with a pool of 20 million hours of raw video.
20 million hours.
But raw video is messy. So the first two stages of the Cosmos platform are all about cleaning and preparing that data.
And it's kind of meta, isn't it? They're using AI to process the training data for the AI.
They are. They use specialized neural nets like Transnet V2 just for splitting video into physically consistent clips. Then they filter out all the noise, the shaky video. And critically, they use a highly optimized VLA model to generate high-quality text annotations for every single clip.
So no more human labelers or simple tags. An AI is tagging its own training food, and they're getting a 10x speed up doing it.
Exactly. And even with all that data, they're smart. They run what they call semantic deduplication, which removes about 30% of redundant video. They want quality and density, not just raw volume.
Okay, so once the data is curated, we get to the video tokenization step. This is where the video gets compressed into tokens the model can actually learn from.
Right, and this is where you can see their commitment to visual fidelity really baked into the math.
Oh, so?
Well, the tokenizer's training objective is to minimize two different loss functions at the same time.
L1 loss and perceptual loss. Let's break those down.
L1 loss is the simple one. It's basically a mathematical ruler measuring, how close the generated pixel's color is to the original pixel's color. It's the pixel perfect part.
Okay.
But they also add a VGG-based perceptual loss, and this is the key. It uses another neural network to judge the generated video not just by its pixels, but by its plausibility to a human.
Does it look right? Does it feel physically real?
So they're optimizing for the human visual system and physical realism at the same time. That sounds like a huge computational burden that VL-JEPA just gets to skip entirely. It is. And what's really fascinating is that Cosmos doesn't just bet on one type of architecture. For its world foundation models, it's actually building two in parallel. Twin engines.
A diffusion model and an autoregressive model. So why do both? Why not just pick one and go with it?
Because their goal is to comprehensively map the entire generative design space. They need to know which architecture is better for which type of physical simulation. Fluid dynamics might be better with one, rigid body collisions with another.
Okay, let's start with engine one, the diffusion model. I like the analogy for this one, the sculptor.
It's a perfect analogy. It's the sculptor because it learns to generate video by reversing a noise-adding process. It starts with a canvas of pure static, and then it iteratively denoises it, chipping away like a sculptor with marble until a clean video emerges.
And training a model this large, we're talking billions of parameters, must be an absolute nightmare for stability.
Oh, absolutely. They use a multi-stage curriculum, starting at low resolution and slowly moving up. They use tricks like query key normalization to control the attention weights, but their most clever move is something called Edel and LoRa.
Wait, LoRa? I thought that was mainly for, fine-tuning LLMs. How does that help with a giant video model?
It's a bit of architectural genius.
Yeah.
By applying low-rank adaptation to very specific layers, the adaptive layer normalization layers, They achieved a crucial 36% reduction in parameter count.
Wow.
It took the model from 11 billion parameters down to 7 billion, with no performance loss.
So even the high-fidelity camp is being forced to hunt for every efficiency they can find at this scale.
You have to.
Okay, so that's the sculptor. Now, Engine 2, the autoregressive model, the storyteller.
Right. This is much more like an LLM. It generates video token by token. It uses something called finite scalar quantization to create a fixed vocabulary of little visual words, and then it predicts the next visual word based on all the ones that came before it.
But that sounds painfully slow, one token at a time. That has to be a massive bottleneck for generating long videos.
It is the main drawback. And to fight it, Cosmos developed an innovation called Medusa speculative decoding.
Medusa?
Yeah, so instead of the big model generating one token at a time, Medusa uses multiple lightweight decoding heads to predict several future tokens all at once, in parallel. Then the main model just comes in and verifies that whole block of predictions in a single go.
That's like when you're talking to a friend and you sort of predict the end of their sentence before they say it, so the conversation can move faster.
Exactly like that. And it gives them huge gains, up to a 3.2 times higher token throughput and way fewer forward passes for the big, expensive model.
And again, I'm guessing they need some serious tricks to keep it stable.
For sure. Normalization and a critical regularizer they call Z-loss, which just stops the numbers from getting too big and causing gradient explosions when they're training on thousands of GPUs.
The technical gymnastics here are just,
Yeah.
it's incredible. But let's bring it back to the core conflict. We have VL-JEPA, the efficient abstract predictor, and we have Cosmos, the massive high-fidelity simulator. They seem to be optimizing for completely different definitions of success.
They absolutely are. Cosmos is all about a pragmatic engineering goal. High-fidelity simulation. Can this replace real-world data collection? That's the question.
And VL-JEPA.
VL-JEPA is a foundational research goal, computational efficiency and abstract reasoning. Can this lead to faster, more intelligent planning?
You can see that difference so clearly in how they evaluate the models. Cosmos literally has to pass physics tests.
It does. They use these highly specific metrics like Sampson error to measure 3D geometric consistency. Asking, is this video a coherent 3D space? They even validate their generations against ground truth from professional simulators like Isaac Sim. They need that physical plausibility.
Whereas VL-JEPA is measured by its speed up, that 2.85x gain, and its ability to do abstract things like zero-shot classification or visual question answering.
It proves its intelligence through concepts. And maybe the most profound difference is in their reasoning mode. Cosmos is, at its heart, a data generator. It's a sandbox for training other AI agents, these downstream policies. The reasoning is indirect.
And VL-JEPA is built for something else entirely.
It's designed for direct gradient-based planning in that abstract latent space. It's sometimes called model predictive control. Because it has a fast, abstract model of the future, it can do deliberate System 2 style reasoning and planning, which is much faster than the slow System 1 pattern matching of autoregressive models.
It's built to think, not just to show.
That's a perfect way to put it.
But you mentioned Cosmos is already finding ways to be more efficient with Adel and Laura. And they even talked about using a diffusion model to clean up the blurry output from their autoregressive one. It sounds like these two worlds are starting to converge.
The convergence is, I think, inevitable. The ideal future architecture is almost certainly a hybrid.
So what does that look like?
Imagine combining the best of both. You have an efficient, abstract, VL-JEPA-like core that handles all the fast, low-latency reasoning in latent space. It figures out the plan conceptually, and then only when a human needs to see the result, or you need to validate it in a high-fidelity environment, you pair that abstract core with a generative decoder, a Cosmos-like engine.
To articulate the plan or simulate the result visually.
Exactly. You think fast, but you speak clearly and realistically only when you have to. It minimizes cost while maximizing both conceptual depth and output quality.
So we've deconstructed the technical blueprints for these AI world models. On one side, the generative digital twin of Cosmos, with its massive diffusion and autoregressive engines.
And its absolute mandate for fidelity.
And on the other, the computationally efficient predictive reasoning of VL-JEPA, with its mandate for abstraction.
I think the key takeaway here for you is that the race for this kind of intelligence isn't just about more data or bigger models. It's a really fundamental architectural debate. Is it better to predict every single pixel to perfectly simulate reality, or is it better to predict just the underlying principles to truly understand it?
You now have the details of how both sides are fighting that battle. And this leads us to our final provocative thought for you to take away. Cosmos, this high-fidelity approach, it still has problems with physical consistency. Things like gravity or fluid dynamics or object permanence, they can still break down in the simulations.
Right, it's a known issue.
So, given that VL-JEPA's entire design forces it to implicitly learn concepts like momentum and gravity just to be able to predict the future state abstractly, could the true scalable solution to perfect physical consistency actually lie in abstract prediction? Rather than just trying to brute force a perfect simulation pixel by pixel, what are the limits of building a perfect digital twin?